start.
This one.
Okay. Rachel mentioned that there might be a few minutes at the start to go over the Peterson et al. 2011 paper. Is that something that we would like to do at this point, or is that something we should do more at the end? How would you like to have the flow of the class?
Let's have your presentation first, because I think that will generate a lot of questions. And do you mind if students interrupt here and there with questions?
Oh, please interrupt me. Yeah, and yeah, teachers, instructors, students, definitely jump in. And maybe Chelsea, I'll let you moderate that. If there are things in the chat that people aren't getting that I'm not catching, please, you can jump in and stop me. Does that sound good?
Excellent.
Okay, perfect. Okay, I will share my screen. I'm more of a Teams person and less of a Zoom person, so let me know if you guys can't see something or if I go astray. So my name, as Chelsea said, my name's Steve Thompson. I'm a practicing consulting geologist. Our firm, it's a small firm called Lettuce Consultants International. We're based in California. I'm in the San Francisco Bay Area, and our company does hazards consulting for large engineering projects. And in my particular focus of practice is in fault displacement hazard and in fault source characterization for doing seismic hazard, ground motion hazard assessment and risk assessment projects. Other colleagues of ours do more classic engineering, geology, landslide hazard, liquefaction hazard assessment type thing. And so I'm extremely excited about this class because the work that, the training that you're getting and some of the work that you'll be doing will directly feed in to improving our models and our ability to do useful hazard, fault displacement hazard assessments for key infrastructure. And the slide here on the introduction slide, this is the Trans-Alaska Pipeline that takes crude oil from the North Slope and Prudhoe Bay through Alaska down to, I think, the Port of Valdez, and it gets shipped off. And at the time the Trans-Alaska Pipeline, or TAPS, was constructed, there was awareness of the Denali Fault and the potential of the Denali Fault to have very large earthquakes, and associated with those earthquakes produce very large displacements. And so the Denali Fault was characterized as a right lateral strike slip fault. And within the lifetime of the Trans-Alaska Pipeline, the kind of big maximum scenario earthquake happened in 2002 with the moment magnitude 7.9 Denali earthquake. And as you can see, we have a before photograph taken not too long after the pipeline was installed. And you can see the really sophisticated mitigation that the engineers put in. They put in a series of bends in the pipe that were specifically designed to be able to have the steel of the pipe absorb that right lateral offset where it crosses the fault. And in addition to the bends in the pipeline, they have these series of skids and a series of bents, or these little frames that prop up the pipeline and place it on top of these bends, place the pipeline on top of the skids. And they were designed to provide a really low friction interface, such that when the ground moved and the pipeline deformed, each in their own ways to accommodate the displacement, the pipeline could stay elevated and not collapse in any one spot and release spill. And one of the really key takeaways from this is this shows that engineering solutions can work. You'll see a slide that shows just how close it came to maybe not functioning perfectly. But key to this class in trying to identify where exactly the active fault traces are, this mitigation had to account for a really large uncertainty zone in exactly where that fault crossing would take place. That really wasn't clearly known, and it remains to be a real puzzle of sorts just because of this particular geomorphic environment. Rich can clarify, but I think there's some large alluvial fans, and the Denali fault, really close to this pipeline crossing, wasn't well expressed in the geomorphology prior to the earthquake. And so that represented a challenge for engineering geologists and designers to try to figure out how to design a mitigation that not only takes into account how much slip we think might happen, but also, in this case, a pretty big uncertainty of exactly where that slip was going to occur. So one of the great examples, and I wish I could study it even more. Okay, so the outline of the talk, I have a few slides that talk in general about how we think about mitigating fault rupture hazard. And then I changed directions a little bit, and I have a set of slides that explain the framework for what we mean or how we go about hazard assessment. And they're both deterministic and probabilistic methods that we use for hazard analysis. And I have a series of slides showing how they're related, how they're different and how they're related. And fundamentally, the Peterson et al. Paper that we read is proposing a useful model for conducting hazard analysis for strike slip faulting. So I hope that these series of slides will help the class and help people understand a little bit more about how hazard analysis is conducted. I have a few slides on the specific PFDHA methodology that Peterson et al. Proposes, and it's kind of the general methodology that we use. And then at the end, I have some slides that discuss more the role of, or the importance of having good detailed maps of active fault traces based on geomorphic criteria, and also the role of conducting pre-rupture fault mapping, the role that that can have on helping us improve our hazard analysis and our hazard models. And hopefully there'll be time at the end for questions. So for how we go about mitigating seismic hazards of all kind, including fault rupture hazard. When we're talking about the built environment, there's this underlying question of what's safe enough. What lengths do we go to make sure that the infrastructure we have, either the buildings that we live and work in, or the linear infrastructure from roads, highways, bridges, pipelines that carry water or fuel, there's always a trade-off between cost and safety. And there's a question, should we be designing our infrastructure to be 100% seismically safe? Should we accept no risk? Should we go to any lengths possible to make sure that the buildings we construct are going to be perfectly resistant from ground shaking and fault displacement? Or do we like our buildings to have windows and decks and neat architectural features? Do we like to design our buildings to be in interesting places? And so we have to make some sort of compromises of cost versus safety. Also, just at what point, how much money do we want to invest in every single piece of linear infrastructure? Are we going to accept that there's going to be some probability that some probability of failure? And it's a society discussion. It especially after disasters, that society discussion gets particularly intense. And it's one that we need to keep having. The engineering community continues to wrestle with it. As far as mitigation options, how do we mitigate fault hazards? The most obvious one, if we're thinking about buildings, is to mitigate by avoidance. So we place our buildings out of harm's way, away from those faults. I think I saw in the syllabus that the class reviewed a planning criteria document from New Zealand that demonstrated, here are the features that you look for of where an active fault is. Here's our recommendation for designing or placing certain structures of different levels of importance away from active faults. And so those mitigation options of avoidance, those are excellent. That's classic. There are many cases where we're not able to mitigate by avoidance. Again, the Trans-Alaska Pipeline is a classic example. There is no way we can route that pipeline to avoid the Denali Fault. And so we need to mitigate by design. And when we're mitigating by design, we need to not only understand where that fault hazard zone is, but we also need to have some way of anticipating or understanding what that displacement amount is going to be. And so here is a side view of the Trans-Alaska Pipeline post-earthquake. And you can see in this particular case that the bent that's holding the pipeline up over the skid, there was very, very little room left over, that the skid almost, or the bent almost jumped off the skid. The engineers say it's extremely likely that the pipe would have continued without any leakage, even if it had completely fallen off the skid. That would have taken several of these bents to have fallen off. But nonetheless, you can see that the design amount is important. So we need to think about the displacement amount when we're talking about design. Another way that we can mitigate is, or another choice, another option is no mitigation, where we can decide that a certain facility, a certain building, a certain piece of infrastructure just isn't worth the cost and effort to design for displacement. We'll accept the risk. And as we know, we accept the risk for faulting often when the activity of the fault is very, very, very low. We decide that it is so low, the chances that it will rupture are basically, we're accepting that risk, they're low enough. Or if the importance of the structure isn't enough, where we can, so if we're building a tool shed, we can accept the risk that the tool shed will collapse if we build it right over a fault. And so an example of fault rupture hazard mitigation, you went through in the class a more modern example from New Zealand that looks like it was a really thoughtfully laid out mitigation plan where it looks at building importance, it looks about criteria for defining a hazard uncertainty location for active faults. Another example from the state of California is the Alquist-Priolo Act. It's an earthquake fault zoning act that was designed to be able to avoid placing structures for structures designed for human occupation to make sure those structures are not placed across active faults. And the important part of this story for the Alquist-Priolo Act, it came in the immediate aftermath of the 1971 San Fernando earthquake. This is an earthquake that happened in the greater LA basin. Much of the surface fault rupture went through neighborhoods and crossed front lawns and underneath foundations. The displacements weren't very large in this area. No structures collapsed as a result of fault rupture, but it was immediately part of the society discussion of, are we going to allow this to happen? And the state assembly passed this law, and now we have in California, we are to avoid building structures for human occupation across faults, but we don't go to the 100% safe criteria. We define a fault that we want to avoid as one that is sufficiently active and well-defined. So sufficiently active, we define that by meaning has it ruptured during the Holocene period, during the last 11, 12,000 years, and well-defined meaning is this fault well enough expressed in the geomorphology and geologic maps such that we would be able to identify it, responsibly zone for it, and set back from it. Okay, so deterministic and probabilistic hazard analysis. I'm switching gears a little bit. Two of the ways that we can think about mitigating when we need to mitigate by design. When we talk about deterministic hazard methodologies, we're often talking about scenarios, and often it's kind of quote the worst case or the maximum scenario earthquake. And so we say we want to make sure that if the worst case, the biggest earthquake occurs, that we can be safe. There's no consideration for how probable that very, very large earthquake is. But there's also the question of, well, if that worst earthquake happens, how much ground shaking is going to occur at your site, or how much fault displacement is going to occur at your site. The amounts, the intensity measures of those deformations, of those ground motions, it really varies from earthquake to earthquake, even one that's going to be the worst case. And so we define safe enough in those situations by needing to define what sort of percentile of the intensity measure are we talking about? Are we going to design for the average or the median, the 50th percentile displacement, where there's a 50% chance given that earthquake occurs, the displacement will be even more, or a 50% chance it'll be less? Or do we want to design for a higher percentile, like an 84th percentile, average plus 1 standard deviation? That would give us more protection. It would be a different way that we could define what is safe enough for a project. So this is kind of how we approach a deterministic hazard analysis. For the probabilistic hazard analysis, including PFDHA, we try to consider all of the plausible earthquake scenarios, and we consider all the different outcomes, all the different possible displacements that would result from those scenario earthquakes. And in probabilistic hazard analysis, the rates of the different scenarios are really important, and we'll see an example of that. And when we talk about a hazard, we're using the summation of the contribution to hazard from all the different scenario earthquakes that can happen at their respective rates and all the different outcomes. And so safe enough, instead of reflecting it in some sort of percentile, are we worried about the median, the 84th, the 95th percentile? Safe enough in engineering design criteria typically is reflected by some definition of the annual frequency of exceedance, or the return period that we're interested in. Many of you may be familiar with building codes where we talk about the 5% in 50-year probability of exceedance, or the 2% in 50-year probability of exceedance. So some slides to show how we go through, or how these two types of hazards are related, deterministic hazards and probabilistic hazards. I'm going
Steve,
through a simple, yeah.
There's a question, what do you mean by exceedance?
Ah, great, okay. So what I mean by exceedance, that's an excellent question. There'll be a slide here soon showing it. And if we think of an uncertainty distribution like this plot right here, where this shows displacement that could happen, in this case, displacement from an earthquake, where we have an average, highest probability sort of average outcome. When I talk about exceedance, I talk about what is the probability of exceeding, of being greater than this particular displacement value. So an exceedance is just an expression of something that would exceed a certain test value that we're talking about. I'll have another example of that I hope will clarify, but that's an excellent question. Thank you. So I'm going through these slides. I'll say also the Peterson et al. Paper, the goal of that paper is to come up with an improved methodology for strike slip faults where we can do these types of hazard analyses. And so again, in this example for a deterministic analysis, our scenario that we'll consider, we'll say, hey, perhaps we're dealing with a fault where we're interested in a maximum scenario magnitude 7 earthquake. And we're interested in what the displacement is going to be from this earthquake. And we have this very crude model, this model that predates Peterson et al. And it's a simple relationship developed by a paper that was Wells and Coppersmith, 1994, where they found a relationship between the log of the average displacement that scaled linearly with magnitude. And you can see down here in this plot, we have moment magnitude on the y-axis. On the x-axis, we have the log of the average displacement from that rupture. And you can see different data points here correspond to different historical earthquakes that have happened. And the symbols are symbolized by the style of faulting. And they can draw an average line, and we can write this expression as a prediction for average displacement. You can see that the average displacement is equal to 10 to the power of, and here's this linear equation with magnitude as being the only predictor variable. So we can use this to come up with an expression of what the average is going to be. And importantly, we have the standard deviation. And here it's in log 10 units, but our standard deviation for our exercise, we're going to use a standard deviation of 0.3. Later in the example, we're going to say that this scenario earthquake has an expected mean recurrence interval of about 1,000 years. So given our scenario earthquake, this probability density function tells us how much ground displacement do we expect to occur on average. The peak of the PDF is just a little over 1 meter, but we can see from the distribution that our model suggests it's entirely plausible to have an outcome where the displacement is only 20 centimeters, or the displacement at any given point might be as great as 70, 60, 70, or I'm sorry, 6 or 7 meters. So there's a huge uncertainty in how much displacement is going to happen. And what we're going to do is we're going to take this probability function, this Gaussian curve in a log normal space, and we're just going to sum from the left to the right, and we're going to show it as a cumulative distribution function. And the stars, these show us, the blue star shows us the average or the median, also in this case, the median expected outcome that has a 50% chance of being exceeded, 50% chance of non-exceedance. And then the green star here shows us the 84th percentile. This is the average plus 1 standard deviation on our uncertainty. And just as we define those in our bell curve, we can define them also in our cumulative distribution function. So again, that median is at the 50th percentile, the 84th at the 84th percentile. Now, we can take the same information from our deterministic assessment, and we can use it or I can show how we use it to build our probabilistic hazard analysis and our probabilistic hazard curve. So this is the exact same plot from the previous slide where we have a cumulative distribution function from this one scenario. And now I'm just going to take the complement of the cumulative distribution and make a CCDF, a complementary cumulative distribution function. And now here's our keyword exceedance. So now we're showing this as an exceedance plot. And how we read it is if we go to a certain displacement, say we go to 30 centimeters, we can go up. And if we read this off, this gives us the probability that this displacement will be exceeded given my scenario earthquake. So we can see up here, 30 centimeters is the equivalent to about a 96, 97% chance of exceedance. Now I'm going to do another trick where I'm going to take this complementary cumulative distribution function that's in a log linear space, and I'm going to make it log-log. I'm not doing anything else, but I'm changing the y-axis to be a log scale. And now we go from this nice curve function to something that is looking more like a hazard curve we typically have in probabilistic analysis. But nothing has changed. This represents that given the scenario happens, the exceedance probability, this is basically corresponding to very, very, very tiny displacements. The probability that that displacement will be exceeded is near 1. So the last step we do to turn this into a probabilistic fault displacement hazard curve as part of a fault displacement hazard analysis is we want to scale this y-axis by the rate of surface ruptures that are expected to occur. So in this scenario, if we're using a mean rate of 1 in 1,000 years, or 1 times 10 to the minus 3, that mean rate coincides with this probability of 1. And so we can scale this whole curve right here by the mean rate of this event, this surface rupturing event happening. And now we have a fault displacement curve. And in all of these curves, we can still track from that deterministic side different percentiles that might be of interest, whether it's the 50th percentile, the median, or whether it's the green star, that 84th percentile, something that's a little more conservative, adds a little extra measure of safety. And so you can see that the 50th and 84th from the deterministic assessment can be tracked all the way to these probabilistic hazard curves. And that's an important note for a lot of engineers to digest when they try to go back and forth with these different approaches. Okay, I think I am slipping behind, so I'll go through these rather quickly. So in PFDHA, there's certain definitions that we need to understand. One's epistemic uncertainty or model uncertainty. And this we express as logic trees in hazard analysis. We don't know which model is the right one. The other expression, the other definition is aleatory uncertainty or aleatory variability, really. This is that maybe we have the right model, but our aleatory variability, that's that natural randomness in a system. An event happens again and again and again, it may not always have the exact same outcome. So I can have many, many magnitude 7 earthquakes, but there'll be randomness in how much displacement occurs at a given site. So we're going to explore epistemic uncertainty and aleatory uncertainty in these next sets of slides. And we're talking about the recipes, the ingredients that we need Peterson et al. To tell us so we can build a hazard curve. So the first fundamental need is we need some equation that will have us, that will give us the mean displacement. And ideally, we'd have a set of different models or different equations that would help us understand what sort of epistemic uncertainty there is about the mean. So up here, we have something called a logic tree, where we have these different branches give us different predictions of what that average displacement would be given our scenario. And so what we're going to do is we're going to go through these different alternatives, and we're going to see the effect that it has on our deterministic probability density function and in our probabilistic hazard curve. So if we go from the starting point, now we're going to go to this high branch value. You can see the curves move to the right. We go to the low branch value. We see the curves move to the left and right. The next fundamental need is an expression of that randomness, that aleatory variability. And here we express this with an example of a logic tree where we have that middle value where we said the variability was going to be a log value of 0.3. We're going to show the result for log 3. Then we're going to vary it. Maybe the correct natural variability is greater, 0.4. A greater standard deviation is going to flatten our probability density function. It's going to flatten our hazard curve. Or maybe the correct answer is something that is smaller. We have less variability. We have more periodicity in the outcome. That's going to result in a peakier PDF and a steeper hazard curve. And then the last one, and this is the one that we're going to get to mostly in this class, is the impact of occurrence rate. What is the rate of these rupture events that are going to happen? And so the middle value of 1 in 1,000 years, you can see that we're intersecting the hazard curve at 10 to the minus 3. If the true rate is double that, we can see the hazard curve jumps up. There's no change to the deterministic analysis, but the hazard curve jumps up. Or if it's actually 1 in 2,000 years is the correct one, the hazard curve will jump down. So you can see the impact of the rate is on the probabilistic hazard curve, but not on the deterministic part of the equation, or part of deterministic analysis. So this is sort of a summary of how these probabilistic hazard curves work, what the different ingredients that we need to build a model and to create a hazard curve, what those different ingredients are and how we can express them in a logic tree, where basically our uncertainty in the mean displacement affects the curve width. The hazard curve will move kind of to the right or to the left, depending on what the mean displacement is going to be. Depending on the natural variability of displacement of our system, that's going to impact the steepness of the curve in purple. And then this mean rate of occurrence, that's going to have a big impact in that it's going to shift our whole hazard curve up or our whole hazard curve down. And yeah, okay, there are all sorts of other things to get into about engineering application of these, but I'll shift. Okay, so now we're going to shift away from kind of the general way we think about hazard and hazard analysis, and we're going to get back to faulting and fault mapping and fault rupture specifically. So here we have a useful terminology that's been developed that Peterson et al. Introduces, and it allows us to categorize different faults that we might end up mapping based on geomorphology. And importantly, we use it to categorize different types of ruptures that have occurred in historical earthquakes. And so we like to separate the idea of principal faulting and principal displacement from smaller amounts of faulting that we like to categorize as maybe secondary, or Peterson uses the term distributed displacement. And then there are other more enigmatic forms of deformation of displacement that we see after earthquakes that we call triggered or sympathetic slips. And in cross-section view, we show examples of these. And so the primary fault and the principal faulting we expect to occur along a fault that is directly linked to the zone of main energy release. And over here to the right in our hazard map, this is an example from Peterson showing the Hector Mine earthquake rupture, where we can see the displacement amounts in centimeters listed. And so the principal zone of displacement occurred along this more linear trace where we can see there were much higher displacement amounts. These secondary faults, these are ones that typically we interpret to have branching relationships with that main zone of energy release. And so they're not going to be carrying as much slip. And you can see examples of that with this trace right here, for example, or maybe there's some of these other smaller ruptures in this view where we expect the slips to be much lower. The last case of the sympathetic rupture, this is one where the mechanism of causing the surface rupture isn't directly related to that main zone of energy release, but might be triggered, dynamically triggered. So now we're going to look at the Peterson et al. PFDHA formulation that's in their paper. And they have their figure 1, it shows the terms that they define, where you have a site that you're interested in calculating hazard for. It's some geographic location XY, and it has some size, it has some area that's defined by kind of a width Z. I'm going to jump to the equation really quickly and try to break it down into component pieces that make sense. So the left part of the equation, I'll say first, is that this is simply an expression of the mean rate, so the annual rate of a displacement occurring that exceeds some kind of test displacement is equal to all the rest of the stuff. So we'll see what it's related to. So the first part is related to the source characterization. This gives us the model that tells us of where the earthquake ruptures are going to be located and what's the magnitude recurrence distribution going to be. So what's the size distribution of earthquakes that we're expecting? Are they going to be magnitude 7s, some variation, some mixture between magnitude 7s and 7.5s, et cetera, and where along the fault are they going to occur? The next term in orange is the conditional probability of surface rupture. So this takes into account that given an earthquake of magnitude M happens, it may or may not produce surface fault rupture. There are many cases of magnitude 6, even magnitude 7 earthquakes that don't produce surface fault rupture. And therefore, this type of parameter is an important consideration in fault displacement hazard that we don't have in ground motion hazard. This is going to be an important impact on our hazard curve, as it affects that rate of fault ruptures occurring. This third term is the main term that your class is addressing. And this is the one that says, okay, given a surface rupture occurs, what's the conditional probability that we're going to get displacement at our particular site of interest? It's not always guaranteed that even if a surface rupture happens on the fault, that it's going to exactly happen at our site. And then this last one is the displacement exceedance part of the equation. This is the one that we would only use if we were using a deterministic hazard analysis. That's the part of the equation that will give us our average displacement that we would expect given our scenario happens, and that will give us also the variability from event to event. Okay, so this conditional—
Wait a second, Steve, just to see if there's questions. One thing I'm always impressed by in this equation is just how much physics and understanding of the mechanics of earthquakes has to go in each part of the equation that you've highlighted. I'm just thinking about for our work in this class and over the past year of how much yeah, information goes into what you've highlighted here in green.
Yeah, yeah, it's definitely all of these components are the current models, like you probably noticed in Peterson. These are empirically based models. We're trying to leverage earthquake ruptures that have happened, and we're trying to make sense of them. And so rather than, or we're trying to evaluate just the statistics of the ruptures that have happened, rather than really focusing on solving these equations using physics-based dynamic models. And so trying to move towards physics-based models is certainly an effort that's ongoing, but in large part, in hazard assessment, it's it's a lot of guessing, a lot of educated guessing, and a lot of just trying to digest whatever data you can get your hands on of past ruptures that have occurred. And especially when we look at that conditional probability of rupture, the main task, or one of the tasks of your class to do the pre-rupture mapping, you'll see how that will really allow us to improve these prediction models of, given an earthquake rupture goes past the fault that's near your site, what are the chances that my particular site is going to experience a rupture? You guys have an opportunity to really contribute to that. Okay, so these are all slides from Peterson et al. And we're trying to break down now this conditional probability of displacement occurrence. And what the effort that Peterson did was an excellent first step. And this straight line is the representation of the fault that was mapped prior to the earthquake rupture. And you can see the solid line versus dashed line versus dotted. That's indicating that degree of confidence in the fault mapping. This straight line, or the wiggly line right here, the solid wiggly line, is supposed to represent the actual rupture that happened following the earthquake. When Rui Chen and her colleagues at Peterson et al. Put this model together, they were working with very few data that were available. They had very, very few examples, but nonetheless, they used those examples to develop these tables that talk about map accuracy. And you'll see this is table 2, and there's an important follow-up table 3 next to it. And one of the things to drive home with this is that the accuracy is, or the ability to understand kind of what the location is going to be of the rupture, it really varies along strike with the rupture. And so here again is an example also from Peterson of different pieces of the 1999 Hector Mine earthquake. And you can see in some areas, the earthquake behaved in a very straightforward sense. It's a relatively simple, straight trace. There's some complexity if we get down to the scale of the tens and hundreds of meters, but roughly it was a fairly accurate trace, or a fairly regular, simple trace. The question is, what does the fault that we would have mapped before this rupture, what does that look like? Would it have been comparably simple? There are other areas just along strike, but here we might be getting into a bend and maybe a little bit more of a structural complexity. But you can see the rupture certainly was quite complex, especially compared to its neighbor up to the northwest. So this is the exact same scale, but you can see we have these near orthogonal faults, we have these other branching faults, we have these curved things. These ruptures really happen. We need better tools to be able to understand where they're going to happen and how much can we anticipate before the rupture, whether it's going to occur here or whether it's going to occur next to it over here. So some other examples of this, these are some slides that Chris Madugo, who's at the PG&E Geosciences Department, he gave a guest lecture at this class last time and showed these slides, and they're fantastic to illustrate our main points of concern.
We saw them also this course.
Oh, you did?
I'm sure it's helpful to go through them, but for short on time, they could be a little bit faster.
Absolutely fantastic. Okay, this is from the Ridgecrest earthquake. The yellow line indicates where a pipeline, a piece of critical infrastructure crosses. And if we just looked at the national Q faults database, these orange lines represent the faults. And so you can see already from the geomorphology that you've been exposed to that these really don't represent in detail where we see possible geomorphic evidence of past faulting. This is purely a matter of scale, and at the scale of our work, we would consider this to be an error. And getting back to Peterson et al., too much of their data that go into their tables represent conditions like this, where really we have small registration errors, we just have a different scale of mapping or map compilation. And so when we look at Ridgecrest and we do a detailed, more sophisticated evaluation of what do we see in the landscape that indicates where the faulting might occur, where are the faults that we would map, we can come up with an image like this, where we can see now this is, we've gotten rid of our errors, and now we're doing something that's subject to interpretation using these different heuristics, the sharp breaks in slope, the linear reaches of drainage, here and here and so forth. And so we have this opportunity at Ridgecrest to now compare that fault mapping that was done with the best available data, and we can compare that to an actual rupture that occurs. And we can do a couple things. We can learn on how to do better and better fault mapping from this exercise, but more importantly for me and the projects that we work on with fault displacement hazard, it gives us an opportunity to say, okay, if I were doing a project for PG&E and I came up with these black lines, what am I going to tell the PG&E gas department as, what is my uncertainty of where the fault crossing is going to be? Where do I expect my traces to occur? Where do I think you're going to be safe? And also questions like, what's the displacement of faulting going to be? So this example brings up some different key questions about faulting. So we have certain examples where we've mapped traces here along these lines, and these are traces that didn't rupture. So even though we've done excellent state-of-the-art or state-of-practice fault mapping, we've seen this clear example here where we have rupture where no fault was observed before, and we have faults that we mapped, which we clearly do think are faults, but they didn't rupture. And so why might they not rupture? And it could be random. There could be just a gap in the rupture. It could be due to just the epistemic uncertainty in exactly where the fault is. And by that, what I mean is this represents one person's interpretation of where the faults are. Maybe this one person's interpretation is incorrect, and in this case, these aren't faults. And another epistemic alternative, another mapping alternative, would have recognized that these aren't faults, but rather this is an important fault, or rather there was something in the geomorphology that a different mapper picked up that suggested that this other line would have been the more probable trace. So
we're going to design or look at a few exercises in the main mapping assignments in this course to work on constraining that epistemic uncertainty based on how faults are mapped by different people.
Perfect. Yeah, so important to maintain independence and try to really develop different epistemic alternatives. That's great. And then the last thing, why didn't surface rupture occur here, is kind of related to this gaps of the rupture idea, but it might be due to aleatory variability in rupture location, meaning that these are perfectly active faults, but maybe they don't rupture in every single earthquake that goes through here. And so it wasn't their turn, so to speak. But the next earthquake might clearly rupture straight down these faults exactly as they've been mapped, and rupture would not occur where it did in 2019. And so these are the extra questions. These are those additional questions that will really help us improve models when we have basically the typical types of studies that we have. Maybe we have a little bit of trenching. Mostly we have these geomorphic interpretations. So the information we need to really update and improve our models, we need more high quality detailed maps of surface fault. Here I say surface fault ruptures, but just detailed maps of active faults, where basically we want to eliminate errors in the mapping due to mistakes like registration, and also, well, I'll stop there. Other information is, this one's really the key, the detailed pre-rupture fault maps, where we want to see how these maps that have evidence of past geologic or geomorphic faulting, how well do they perform against actual ruptures when they occur in detail. Other information that would help would be, as we get more and more paleoseismic data, I would love to have paleoseismic experiments go out to places like Ridgecrest, excavate trenches in areas where no previous faults were mapped, and just ask those questions from a paleoseismic trench standpoint. Is this really where ruptures continually recur, but the geomorphic processes in this area are such that we just erased our evidence? And so we really, based on our geomorphic mapping tools, we really don't have a good chance to define these in the future. And then obviously all of this will lead to more explanatory variables in our model. I think I'm gonna stop there. The other slides I have show concepts of how Peterson et al. In their model, how they develop their specific models of conditional probability of displacement occurrence. I'm sorry, I just said I was going to stop. One more point. The main method that Peterson et al. Used is they took the ruptures after they occurred, and they developed these grid systems over the ruptures where they occurred. And then they did a box counting experiment for cells surrounding the ruptures, and they used those to develop the probability that there would be rupture at a certain distance away from the principal fault. So in this example, we have a simple trace. The principal fault would have been defined by Peterson right up through the middle, develop a grid system. And you could see in this reach of the fault, the probability is next to 0. That if your site was located more than 100 meters or so away, the conditional probability would be 0 in these reaches. But in these areas of complexity, if they define their principal trace to be something like this, and they set up a grid system, there would be a non-zero conditional probability that you would get a displacement in a cell if you were 200 meters away, 400 meters away, etc. And so they built their models only using post-rupture data. They weren't able to incorporate pre-rupture data. And so the final kind of thing to drive home is this figure, where in the future, we want to be able to develop our conditional probability models based on grid count methods or other methods, where we really want to center the grids on what we mapped prior to the ruptures, and then compare what we see prior to the ruptures with what actually occurred. And we want to test things like, in the places where we map secondary faults, what's the likelihood that they're going to produce a secondary rupture when the earthquake actually happens? Or what's the chance that the rupture is going to go somewhere else? And then kind of the same thing, when we map with apparent confidence where a principal fault will be, what's the uncertainty that the principal rupture might be in a completely different location? and how can we build better models about the likelihood that they would be a certain distance away. Okay, so I'll stop there. I'm sorry about my time management. I didn't move through early slides quickly enough, but basically we went over hazard mitigation and the ways that engineers in the engineering community wrestles with what's safe enough. We looked at a couple of different types of facilities. We looked at lifelines, and then we had an example of an apartment building, but there are other discrete facilities. We talked about mitigating by avoidance or by design. We looked at some slides of different methods, deterministic and probabilistic methods for displacement hazard analysis and how they're related. And then we looked at some of those elements that go into a probabilistic hazard analysis with a focus on this conditional probability of whether rupture is going to happen at your site. Okay, so thanks. I will stop there.
Thank you very much, Steve. I think really, really well motivates a lot of the work that we're going to be doing in the semester, as well as some of the analysis that some of us will be doing after the course. So we have 13 minutes left. So I'd like to open the course up to the students to ask questions to Steve. And so ideally just unmute yourself and say your questions out loud, or if you'd prefer, you could put it in the chat and I'm happy to read it. So
I have a question.
Yeah.
So you were just, okay, there's not much feedback. You were just talking about how you wanted to integrate the pre-rupture mapping with post-rupture mapping. Have you done mapping in areas you think are likely to have earthquakes since Peterson et al. Has come out to get that pre-rupture mapping in preparation for a possible earthquake?
That's that's an excellent question. One of the things the broader earthquake hazards community has done for a while now is they've tried to prepare for the next earthquake with pre-rupture maps, not so much specifically for hazard analysis, but gosh, Ramon or Rich, you could probably help me out. It was a while ago that there was a large NSF-funded EarthScope project that started to systematically collect LiDAR data along all the major active faults through the San Andreas plate boundary. And Ramon has probably undergone this in his lectures. Obviously, since those initial LiDAR surveys of the main faults, several of them have been resurveyed with much higher quality mapping. And the US Geological Survey has released small grants throughout the Bay Area where researchers wouldn't naturally necessarily go, but they've released grants for people to update strip maps at a high resolution to basically map out whatever traces and trace complexities they can. And so that's sort of crowdsourcing is what we're currently relying on as our improvement of pre-rupture mapping. One of the, you bring up a really good point that it's pretty haphazard right now. If a consulting group does a project, for example, for a certain utility, like the California Department of Water Resources and the California Aqueduct, there will be little bits and scraps of strip mapping done at a very detailed level where those aqueducts cross faults like the San Andreas. But there's really, those kind of get buried in reports for DWR or for the other clients. They're really not brought into the community. The mechanism to do that is something that the California Geological Survey is trying to do with curating the Q fault mapping data set So they're trying to constantly update and improve Q faults, but it's an extremely labor-intensive process to come up with an update of mapping in one particular area, bring that to the attention of Judy Zachariason at California Geological Survey. She needs to find time to review, approve, incorporate that into the California faults, and then pass that on to the US Geological Survey in their updates. So I wish we could be doing more to prepare, but it's pretty haphazard. Ramon, do you have any other thing to build on that?
Well, yeah, luckily there's a lot of high resolution topographic data coming out. So there was the GEO EarthScope effort in the mid 2000s that you referred to, but now through the USGS 3D elevation program, most of the US will be covered probably in the next couple of years, at very high quality LiDAR point counts. So there's going to be a great opportunity to revisit. Sorry, I'm about to sneeze. Sorry about that. There's a great opportunity to revisit all these fault zones and try to be really systematic. And that's why I'm excited about this class. I think, one of there's a lot of things to think about. One is also just, is there any semi-automatic opportunities for scanning these data? And that's something we've started to play around with, sort of topographic metrics. Could we find ways to kind of draw attention to fault zones so that then we could bring the human element in a little later in the process. The other thing, for this class, and it's a big challenge, is dealing with that practitioner variation. So hopefully most of the experts get the same answers, but that's not always true. And so how do we develop this expertise in a more systematic way? And what are the guidelines? Because mapping faults it's kind of a fault zones is sort of a specialized mapping activity. You can expect a geologist will map in a fairly uniform way, but map, the bedrock as well as maybe some of the geomorph. But how do we train up people in this particular area? And I think it's challenging, but super interesting.
Yeah.
One other point is we've made all these GIS files for you to standardize both the mapping and the geomorphic, for noting the geomorphic evidence that you use for faulting. And go a little bit back to Steve was talking about, one of the challenges is just collecting and publishing these data. And so we're hoping that by having this very standard protocol that you're going to put quite a bit of time to learn how to use, this will then make it easier for other people to at least easily look at and understand all the mapping products that we've made from this course.
Yeah, perfect. So one other point with that when we have tried, we're currently working on this pretty ambitious project with UCLA to do a fault displacement hazard map of California, and it's really going to be an interesting experiment. So it's one of those things where you want to put it out there knowing that it's wrong, and you want people to you want it to be improved right away from kind of the crowdsourcing idea. But one of the most frustrating parts that I've found with going from really nice detailed fault mapping is the current fault maps, like what you get in the Quaternary Fault database. The classification is purely based on activity, and oftentimes it's grouped. And so if you are mapping along the San Jacinto Fault or the San Andreas Fault, you could have a beautiful through-going, perfectly expressed trace that you have high confidence is where principal faulting will occur. That will have the exact same attribute field and classification as a tiny 20-meter long splay fault that someone just happened to map, that if it's correct is very likely going to accommodate a much lower secondary amount of displacement. And so having in the mapping that would really help with our hazard modeling is ways that we can introduce to the classification, we think this is a principal trace, and ideally why. And then we think this is going to be this is a secondary trace where secondary deformation is more likely, and this is why. And then following the rupture, we can start to test those. How good are we at really anticipating where principal slip's going to occur versus these secondary slips? So that's just another thing to think about that would be incredibly useful to us.
So yeah, on your mapping, as you will see, we indicating the confidence rank as well as if faults are primary or secondary.
Perfect. Yeah. Yeah. And you know, it's a different thing to think geologically. Is this a primary fault? Is it a secondary fault? It may not correlate perfectly with when a rupture occurs, where the principal slip is going to be and where the distributed slip is going to be. We get surprised all the time. But until we show that and make those, you know, the test for it is for us to start producing those fault maps. Like you say, Chelsea, you know, what's our confidence? Do we think it's primary, secondary? That's going to allow us to really test to see if our slips, when they do rupture, is this where the principal slip's going to occur versus the distributed slips that engineering community cares less about if you have an extremely strong steel pipe going across, for example.
So I want to add, doing this pre-rupture mapping and then comparing it to these later ruptures, you'll see it's doing high quality pre-rupture mapping is really challenging. And even the maps produced by professional geologists with local expertise do not get it right all the time. And so really just want to keep in mind that the task that you're doing in this course is hard, but we're looking at ways to improve our abilities to do this, and as well include this extra information about the faults that we've mapped.
I have a question. When you're doing when you have variation in the pre-rupture mapping between like different like experts maps, is that an expression of how well defined a fault area is?
That's a great question. It's a luxury when we have alternative interpretations in an area that are due to just differences in professional opinion, you know, mapping at the same scale. Oftentimes, one of the first steps we do is often we compile all of the available maps that have gone through an area. And so if we're in the Hayward fault, we will, you know, there have been 4 or 5 different published maps of the active Hayward fault zone, and we'll compare all of those, and we'll compile all of the different trace interpretations. And our evaluation of that commonly includes, okay, what was the scale of the original mapping? You know, are there some that were compiled from a really small scale map and we kind of throw that out? But also it really is striking. Often you're right. Often it's because there's very poor geomorphic expression in that area. And so there's a lot of uncertainty, and people might just come into that area from the north or from the south when they see a certain pattern or whatever. Or they might just have their own different rules of thumb, their own different heuristics for what do you do in these cases where there's no clear expression. And the way we treat those in an assessment is typically we will just try to bound the edges, and we'll just say in this location there's that much wider of an uncertainty zone of where the rupture might occur. And if you're a housing development, you might have to set back even farther than you normally would if a fault was perfectly well defined. Or you might have to pay extra for a site-specific trenching study to try to narrow down which, you know, where exactly is the fault? Which of these traces were just incorrect and which of them might be more correct? Does that answer your question?
Yeah, thank you.
But yeah, but we actually love it. If we go into a project and there's only been one prior map available, there's a tendency to say we have one trace, our uncertainty is less. Look at how confident we are. There's one trace. And the mistake, the trap that we fall into is we have narrow uncertainty zones where what we should be doing is we should be really broadening these uncertainty zones because we haven't accounted for all the other people who haven't mapped the fault, who might map it in completely different places. Does that make sense? So it's a big challenge for us when we don't have alternative maps. We have to play that game of like, okay, how big should the uncertainty zone be?
Great, thank you very much, Steve. We are actually already a couple minutes past the end of class. And so yeah, it's been so great to be able to hear from you today and for you to really motivate this work that we're going to be doing in this class from your longtime experience in this type of work. So yeah, it's the end of class.
Yeah.
If anyone has any questions about the homework, I can stay for a few minutes, but we should finish fairly soon.
All right. Well,
Thanks a
I'll
lot,
say,
Steve.
yeah,
Appreciate it.
yeah, thank you. I'm
Thanks
so
a lot.
excited about this class, obviously. So yeah, thank you for all of you for signing up for the class and working hard at this.
Thank you.
All right.
Excellent. See you soon.
Do you have a question? Oh no. Dominic, do you have a question?
I think he might just still have his computer up from being in class at UNR.